Okay, I got the little, yeah, it is recording. And um, this should be a link to the OneDrive notebook um, because as I write, things disappear from the screen quickly. Um, okay, any questions or comments before I get started? All right, we'll get started. Feel free to come off mute and interrupt me at any time if you do have a question, because I guess I tend to look down at the where I'm writing and not necessarily at the screen. Um, and then, of course, at the end, I'll turn the recorder off and you can ask questions that won't be recorded. Um, so, all right. The the goal of today is that every von Neumann algebra can be decomposed into von Neumann algebras of three different types. Uh, right. They're, for lack of a better name, just called type 1, type 2, and type 3. And then each of those can also be subdivided into types as well. And we'll get into that a little bit. Um, so there's kind of a lot that can be said, and definitely more than one lecture could be given on type decomposition. So I'll be following section 4.3 of the notes, but probably omitting proofs as I run out of time. And yeah, just to maybe keep with the narrative structure. I don't know if you had a lecture on section 4.2, but I think just two definitions that appear there that are going to come up a lot is that what a abelian projection and a minimal projection is. So a projection is abelian if this compression PMP is abelian. And P is minimal if this compression is just equal to the complex with this projection out front. And so, of course, a minimal projection will always be abelian. So those are just some definitions that were in 4.2 that are definitely going to come up. And so, right, how we do this type decomposition is you classify von Neumann algebras by the types of projections they have. So the first sort of step in that is, defining the types of projections we have possible, and then we'll talk about when they show up. So now definition 4.3.1. So we take von Neumann algebra M and B of H. And then we're going to say what types of projections are possible. We say P is finite, and M if for any projection Q sitting under P, that is additionally equivalent to P, then this is going to imply that P equals Q. And then Q is another projection. We say that a projection is semi-finite in M if there exists a family of projections indexed by I, and they should be pairwise orthogonal and finite. Such that they sum up to P. So given any projection, you can find orthogonal finite projections that sum up to it. We have that a projection is purely infinite. And M, well, it has to be non-zero. And there does not exist any non-zero finite projections. Sitting under P. And then we have properly infinite. And M if P is non-zero, and for all non-zero central projections, so the center, then ZP is not finite. And then we say that M, basically M is finite, semi-finite, purely infinite, etc., if the identity 1 holds that property. If 1 has that property. Okay, so it's 4 different types of projections that we've defined. And I guess there are some implications of these definitions. You always have that finite implies semi-finite implies not properly infinite. And then we have purely infinite implies properly infinite. Okay, and so now kind of work on some intuition about von Neumann algebras that we've looked at that have projections with these properties. So I guess maybe first kind of example is that for abelian von Neumann algebras, right, projections are equivalent if and only if they are equal. This is an exercise from 4.1. So abelian projections are finite. Okay. And then maybe another sort of fact that directly follows from these definitions is that a factor is either finite or properly infinite. Okay. And so now some more examples to work with these new definitions. So we'll just look at bounded operators on a Hilbert space is our von Neumann algebra. Projection there.
Sorry to be rude and interrupt. Can you scroll back up?
Oh, yeah.
That first set of implications, the last one should be not purely infinite.
Oh, thank you. Yes, that is correct. Thank you. Yes, please interrupt whenever you feel like it. Um, cool. Um, so any finite rank projection is going to be finite. Uh, Rank is finite. And so the idea here is that suppose you have a projection Q sitting under P. This means that the subspace QH is inside P of H, and this implies that Q is finite rank. If, moreover, you have that Q is equivalent to P, and V is the partial isometry such that P star V equals Q and V star equals P, then an earlier exercise basically just tells you the trace of a finite rank operator. It's going to be the dimension of the Hilbert space. We have that dimension of QH equals the trace of Q. Then you write out it as V star V. Then you can use the permutation property inside the trace to get the trace of P, which is then the dimension of PH. And that implies that QH equals PH and Q equals P. And so maybe moreover, if dimension of H is finite, then the identity is a finite rate projection. And also, and hence finite. And that means for finite dimensional Hilbert spaces, B of H is finite. Okay. So keeping on this, with this example of M being bounded operators on a Hilbert space, if the dimension of pH is infinite, then P is not finite. And to see this, so take an orthonormal basis inside pH. And then we want to take disjoint subsets with the same cardinality as E. Right, you can do this since they're infinite. Uh, then if we take Q to be the projection onto the closed span of this first subset, um, then Q is equivalent to P. So there's an exercise for this. Um, but Q is less than P, and it can't be equal since P minus Q is then the projection onto the closed span of E2, and that's not zero. Um, and right, so that shows that P is not finite. And um, since B of H is a factor, uh, these projections are always properly infinite. Okay. Um, and so we'll get more work with these definitions as we keep going. Um, and so do a a proposition that's sort of inspired by the idea of in linear algebra that that a matrix is going to be invertible if and only if it's both left and right invertible. And so that works in a more general setting. So it's a nice property of finite von Neumann algebras. So von Neumann algebra M is finite if and only if all isometries are unitaries. Uh, so go ahead and prove that. Uh, suppose M is finite and let V and M be an isometry. So in particular, V star V equals 1. Um, and we have then that V star sits under 1. And then by finiteness, this implies that V star equals 1. And so V is a unitary. Now, conversely, if we assume every isometry is a unitary, and suppose that P is sitting under 1 and P is equivalent to 1, uh, then we let V be the isometry that is fine. Well, I guess we're the partial isometry right now. V star V is 1 and V star equals P. Um, then V is an isometry and hence a unitary. Uh, Therefore, P V V star equals 1. So 1 is finite in M. So this is the shows that for a finite von Neumann algebra, um, you can characterize it by saying all isometries are unitaries. And yes, okay. So I'm going to state a few propositions that get used in the proofs of the larger theorems. And I think because of time and the narrative arc, I'm not going to do the proofs, but let's just put the statements down so we can use them. Uh, so for von Neumann algebra, um, we look at the two projections. Uh, if P is subequivalent to Q and Q is finite, um, respectively purely infinite, uh, then P is also finite. Right, the same property holds for purely infinite. So for now, we're just taking this proposition as a property that subequivalence of non-zero projections, then the subequivalent projection inherits being finite or being purely infinite. Um, okay, another property that we want is a different way to characterize being semi-finite. Um, so again, looking at just a general von Neumann algebra. Um, so projection is semi-finite, right? Recall that just means it's the sum of orthogonal finite projections, if and only if it is a supremum of finite projections. Um, we also have the supremum of semi-finite projections is again semi-finite. And subprojections of semi-finite projections are semi-finite. So this becomes like a useful property in some proofs that you can work with supremums of finite projections instead of the sums of orthogonal ones when you are dealing with semi-finite projections. Okay, so now let's define, now that we've discussed a little bit about the types of projections, we can define the types of von Neumann algebras that there are. Well, every von Neumann algebra can be decomposed into. So von Neumann algebra M is type 1 if every non-zero projection has a non-zero abelian subprojection. That will be type 2 if it is semi-finite and has no non-zero abelian projections. Also, it means it won't have any minimal projections because remember, minimal projection means that the compression is isomorphic to the complexes, and that's always abelian. And type 3, if it is purely infinite. And just remember that we're saying a von Neumann algebra M has these properties if it's the identity operator in there, the one inside M has these properties. And so let's give some examples of these three types of von Neumann algebras. So an abelian von Neumann algebra is type 1. Bounded operators on a Hilbert space is type 1. Or I guess so. For the reason for the first one is that all projections are abelian inside an abelian von Neumann algebra. So of course, there's always a non-zero abelian subprojection. And so for the reason why B of H is type 1 is that any non-zero projection has minimal, hence abelian subprojection of the form C tensor conjugate for any unitary or for any unit vector. In P of H. For type 2, we'll go into this a little bit more later, but a group von Neumann algebra for a countable discrete ICC group is type 2. And say more later. And the goals notes don't really elaborate much on type 3. I do see on the schedule that there'll be something on Tomita Takasaki theory later. So type 3, I think I won't say any examples now. I think you'll be given more at a later time. I think I would just be confusing if I said some of them. Okay. Um, so we're working towards this type decomposition theorem. And to motivate that, um, I guess we sort of start with an observation that, where I just said there's these three types of von Neumann algebras, gave examples of two of them. Um, but so an observation is that um, a von Neumann algebra M does not have to have a type. And to sort of to motivate this, uh, kind of do an example. So let M1 be type 1, M2 be type 2. Right, then M1 direct sum M2 does not have a type. So to see this, so it's not type 1. And we look at a projection P for M2, then 0 sum P is a projection for direct sum of these two. Um, and it has no non-zero abelian subprojections, because this P is coming from M2, and that's the definition of being part of the definition of being type 2. So the sum cannot be type 2 or cannot be type 1. And the sum of these two von Neumann algebras cannot be type 2, because now if we start with an abelian projection from M1, then some 0 is sitting inside. There's a projection for the sum again. And it's still a non-zero abelian projection. So then it can't be type 2. And it's also not type 3. Um, right, because the same P sum 0 is finite by virtue of being abelian. So, okay, M1 sum M2 does not type 1, type 2, or type 3. However, if we just, right, however, take Z1 to equal 1, 0, and Z2 to equal 0 plus 1. Then if we look at this compression, M1, direct sum M2 compressed by Z1, it's going to be isomorphic to M1, and M1 sum M2 compressed by Z2 is isomorphic to M2. So what this shows is that while the direct sum of these two von Neumann algebras doesn't have a type, there's exists projections that the resulting von Neumann algebras, the compressions, are of type 1 and type 2. And that's really the point of the type decomposition theorem, is that any von Neumann algebra can be decomposed uh, into compressions of these three types. And so that's we'll do that theorem now. So for any von Neumann algebra, uh, there exists unique orthogonal central projections Z1, Z2, and Z3. Right, they're central, so they're in the center of M, such that they sum up to 1, and MZT is type T for each T in, right, 1, 2, or 3. And so because of this theorem, that's why people talk about saying a von Neumann algebra has to be of a type 1, type 2, or type 3, because any von Neumann algebra can be decomposed into a direct sum of these types. And so then when you're classifying, it makes sense to then you just need to understand up to what type it is. So let's do the proof of this. So we're going to start with the type 1. So Z1 be the supremum of all abelian projections in M. Now, since conjugating a projection by a unitary still gives you a projection, so for any unitary U, um, and any projection P. What this means is that uh, conjugating the supremum of the abelian projections still equal to itself, right? Or we could say that this supremum of abelian projections commutes with all unitaries. And then since every operator in M can be written as a linear combination of 4 unitaries, this implies that the supremum projection is in the center of M. Okay. And so now the claim is that the compression MZ1 is type 1. Okay. So prove that. Suppose P is sitting under Z1 and is non-zero. Then by definition of the supremum, there exists an abelian projection R such that PR is not zero. And right, this is going to imply that PMR is not zero. And an earlier proposition from section 4.1 tells us there exists P non-zero such that, well, P0 sitting under P is equivalent to R that's non-zero sitting under R. And then it's going to follow from proposition 4.2.7 implies that P0 is abelian. So this compression is type 1. Okay. So now let's move on to the Z2. So now let Z2 be the supremum of all finite E and M projections that is sitting below 1 minus Z1. And then by the same conjugating by unitaries arguments we had for Z1 by previous argument, we have that Z2 is also in the center of M. And so by proposition 4.3.5, which was one of the ones I wrote down but didn't prove, it's saying that being the supremum of finite projections is going to also be semi-finite. So that's the point here. Now, since Z2 is under 1 minus C1, this means it has no non-zero abelian subprojections. And so that means MC2 is type 2. Okay. And so then we just have the type 3 to deal with. So we just define Z3 to be 1 minus Z1 minus Z2. And observe that any finite projection in M lies under Z1 if it is abelian. Also, and then otherwise, the finite projection will lies under Z2. And what that means is that this Z3 has no finite subprojections. And then, so MZ3 is type 3. So far, we've shown that there exists orthogonal projections such that this property holds, but we still need to show uniqueness. Um, yeah. Okay. Actually, I think I'm going to leave that because there's still more stuff I need to talk about. Decomp. Okay, so we're just going to put a pen in uniqueness. Okay. So I think the first sort of right observation that we have, right, I'm going to put the box there even though I didn't quite finish the proof. Right. Since these projections are central, we had that exercise 4.2.2 tells us that M is isomorphic to the direct sum of these compressions. Um, and this right tells us that all von Neumann algebras can be written as a direct sum of type 1, type 2, and type 3. And an immediate corollary we get from the type decomposition theorem is that a factor, right, meaning trivial center, is only one type. One or type 3. And the proof of this is that, well, if you have trivial center, then the only central projections of a factor are 0 or 1. So when you look at this decomposition, C1 plus C2 plus C3 equals 1 by the type decomposition theorem, this implies that only one of these is 1 and the rest is 0. Okay, so a factor will always have a type. Um, and some non-trivial facts. So uh, that von Neumann algebra, so M is type T if and only if its commutant is type T. T being any of the three types. And then um, the uh, compression preserves type as well. Okay. Um, all right. Skipping lots of proofs and still there's so much more to say. Okay. So we'll try and talk about how each type 1 and type 2 can be decomposed further, um, starting with type 1. So, uh, so if we assume that M is a type 1 von Neumann algebra, um, then for any natural number, we say M is type 1n if there exists um, projections that are non-zero orthogonal equivalent and abelian such that they sum up to 1. Um, and then M is type 1 infinity if you need an infinite family to do this. Um, and a type 1 of von Neumann algebra can only be either type n or type infinity, it can only be one type. Um, and then examples, abelian von Neumann algebras is type 1, 1. And then uh, finite dimensional matrices are type 1n. Um, and that was kind of the other big theorem in this section that don't have time to prove. It's definitely worth looking at. That if M is a finite type 1 von Neumann algebra, finite type 1, sorry, factor, restricting ourselves to factors, then M is isomorphic to Mn, the complex, um, the square matrices over the complex numbers. Right. And so the proof of this is in the notes, but at this point we can basically just say what all type 1 von Neumann algebras are. You have, when it's not a factor, right, with a abelian case, then you have a type 1, 1. Yeah. Um, then finite type 1 factors are just the matrix algebras. And then the 1 infinities is B of H for H infinite dimensional. And that proof is not in the notes, but it's similar to the complex matrices case. Um, so I guess I'll quickly say something about type 2 von Neumann algebras. So a type 2 von Neumann algebra is type 2, 1 if it is finite. Remember, a type 2 von Neumann algebra is semi-finite plus no abelian projections. And so now you restrict it further to being finite and no abelian projections. Non-zero. And then type 2 infinity, if M is properly infinite. And so the right, really the quintessential example of a type 2 1 factor is the group von Neumann algebra for a countable discrete ICC group gamma is type 2 1. Moreover, it's a factor. So definitely go through that example and the little exercises in it. It's really important to see that, and it's not too bad to go through. And then uh, turns out that all type 2 infinity factors, right, it's the key there, are of the form M tensor B of H, where M is a 2, 1 factor, and H is infinite dimensional. So I think I've ran out of time, so I will stop recording.